Hello students, welcome to the 7th session of electrochemistry. In this session, we'll discuss about the Nernst equation, its derivation from Gibbs free energy, the relationship between the cell potential, Gibbs free energy and equilibrium constant. We'll also go through the numerical problems to understand the application of Nernst equation. Now let us understand Nernst equation. What is the need for the Nernst equation? We know that standard electrode potentials are measured in standard states. That is, when the concentration of the electrolyte is 1 molar and the temperature is 298 Kelvin. In actual practice, the electrochemical cells do not have always the fixed concentration. So the electrode potential depends upon the concentration of the electrolyte solution. Well, the Nernst equation gives the relationship between the electrode potential and the concentration of electrolyte solution. Nernst equation gives the relationship between the electrode potential and the concentration of the electrolyte solution, so that we can calculate the electrode potential at various different concentrations. We can derive Nernst equation from Gibbs free energy, that is delta G. You know what is Gibbs free energy? Well, it is the free energy that can be converted into useful work that we have studied in our thermodynamics. Delta G is also related to potential difference. Well, the equation is delta G is equal to minus NFE. If it is delta G0, then it is minus NFE0. That is under standard condition, where N is the number of electron, F is the Faraday, and E is the potential difference. Since delta G0 is equal to minus NFE0, hence we can say that if cell potential is positive, then the reaction is spontaneous. Because for the condition for the spontaneity is decrease in Gibbs free energy, or delta G being negative. We can equate the Gibbs free energy change under non-standard condition and standard condition as follows. Delta G is equal to delta G0 plus RT ln Q. Now on substitution of the equation that we have already seen, delta G is equal to minus NFE into the above equation, we will get this when the equation is divided by minus NF on the both side, our equation reduces to E is equal to E0 minus RT NF ln Q, where ln is the natural logarithm. If you convert that into log to the base 10, the equation becomes E is equal to E0 minus 2.303 RT divided by NF log Q, where Q is the reaction quotient. You remember the reaction quotient? You might have studied reaction quotient in your previous year chapter equilibrium. The reaction quotient has the same expression as the equilibrium constant. The only thing is that the concentrations are before attaining the equilibrium. Okay, so this reaction is very important. E is equal to E0 minus 2.303 RT NF log Q. Now in the equation, E is equal to E0 minus 2.303 RT divided by NF log Q. There are two variables. One is concentration and the temperature. Now if we can keep the temperature at 298 Kelvin, which is quite simple because we can always air condition our laboratory to such a condition, that is at 25 degrees Celsius, then the factor 2.303 RT divided by F is basically a constant, because 2.303 R is the universal gas constant, 8.314. Temperature is again fixed to 298 Kelvin, and F, you know, it's 96500. Now if you get the value out of it, it comes out to be 0.0591 volt. Therefore, our equation is further reduced. Now we can write the equation E is equal to E0 minus 0.0591 divided by N log Q, where N is the number of electrons involved in the redox reaction. Q is the reaction quotient. E0 is the standard cell potential, and E is the non-standard which has to be calculated. Okay. Now as the redox reaction proceeds, the reactions are consumed and the product are formed. The cell potential, that is non-standard cell potential, will decrease till the equilibrium is reached. At equilibrium, delta G will become equal to 0. Therefore, the cell potential will also become equal to 0. And the Q, equilibrium constant, will become equal to Kc, because the reaction has reached the equilibrium. Now if you substitute this into the Nernst equation, we'll get this: minus delta G0 is equal to NFE0, which is equal to 2.303 nRT log Kc. And this is a very important equation because it connects the electrochemistry with thermodynamics and kinetics. That is, this equation connects equilibrium constant, Gibbs free energy and cell potential. Now let us consider a general oxidation reaction. Okay. And you try to apply the Nernst equation for this. In this we have to substitute for Q. Q is reaction quotient. Remember, reaction quotient has same expression as that of equilibrium constant. So we can write this equation as E is equal to E0 minus 0.0591 divided by N log into concentration of M raised to N plus. Now let us put this equation into a Daniell cell. When the conditions are non-standard, that is, when the concentration of the electrolytes are not 1 molar. In that case, you will get E is equal to E0 minus 0.0591 divided by 2, because here N is equal to 2. The number of electrons involved in this reaction is 2, and the Q will be the concentration of zinc ions divided by the concentration of copper ions. So that is how we apply the Nernst equation into a redox reaction. Now let us understand what are the applications of Nernst equation. The Nernst equation can be used to determine the cell potential of a non-standard cell. Suppose you have been given a cell in which the concentration of the electrolyte is not 1 molar. So here is an expression for the cell, that is cell representation. The concentration of Mg2 plus ions is 10 raised to minus 3, and the concentration of copper ion is 10 raised to minus 4. Standard reduction electrode potential of magnesium and copper is given. To write the redox reaction, you should know what is the expression for Q. It is the concentration of product divided by the concentration of reactant, which comes out to be the concentration of magnesium divided by concentration of copper. So if you apply this, you will get E cell. E cell is equal to 2.68 volt. So we can determine the cell potential of a non-standard cell. It's one of the application of Nernst equation. This is another problem in which we are calculating the EMF of a non-standard cell. So here you first write down the Nernst equation. The number of electrons involved is equal to 2. So N is equal to 2. We know the E0. E0 is 1.05 volt. The Q is concentration of nickel divided by the square of the concentration of silver. Now if you substitute, you will get this, and using this you can calculate the E cell of a non-standard cell. The second application is to determine the standard Gibbs free energy and the equilibrium constant. Gibbs free energy and the equilibrium constant. So the question is, calculate the standard cell potential of a galvanic cell in which the following reaction takes place. E0 of cadmium is given, E0 of chromium is also given. Using this, we can calculate E0 cell, which comes out to be 0.34 volt. Since E0 cell is positive, we can say that the reaction is spontaneous. Delta G0 is equal to minus NF E0. Therefore, you have to simply substitute for this value. N in this case is equal to 6. The number of electrons involved in the reaction is equal to 6. So we calculate delta G0, and from the delta G0 we can calculate the equilibrium constant, because delta G0 is equal to minus 2.303 RT log Kc. The third application is the working principle of pH meter. It is based on Nernst equation. Now, in order to understand, we are going to do a problem. Calculate the potential of hydrogen electrode in contact with a solution having a pH equal to 10. The pH meter actually works the other way around. It determines, or it shows the pH based on the potential of hydrogen electrode. Here we are trying to determine the potential of hydrogen electrode if the pH is equal to 10. First, we'll write the equation for the reduction of hydrogen. H plus ions plus electron gives half H2. Then we write the Nernst equation, and we know what is Q. Q is equal to 1 divided by concentration of H plus since pH is equal to 10, therefore the concentration of H plus is equal to 10 raised to minus 10, which on substitution you will get the answer.